Hi everyone, welcome back. In this video, we're going to be finishing up our discussion about electron configurations and see how those apply to elements on the periodic table. Pause the video now to read over the learning objectives listed here on the bottom of the screen to make sure that you understand where we'll be going with this information. Let's review a little bit what we saw last time about the orbitals within single and multiple electron atoms. On the left is what we would have for a single electron atom. And what we see is that orbitals within the same shell have the same energy level. In other words, they are degenerate. However, elements with multiple electrons end up having splitting that occurs, and that's due to differences in the effective nuclear charge between orbitals that are within the same shell but different subshells. So in other words, the Z effective for 2s is going to be larger than that of the 2p. And that means that those electrons in the 2s are closer to the nucleus and lower in energy. This brings us to what we call the Aufbau Principle, which is German for building up. And it states that in the ground state, orbitals are filled sequentially, starting with the lowest energy orbitals first. And you've seen this diagram when you did your reading in the ebook that illustrates the order in which we fill up the orbitals. It starts with the 1s, then the 2s, then the 2p, then the 3s, etc. It just simply follows going up vertically on that diagram that we showed on the previous slide. And so if we apply this and we look at the elements on the periodic table, we can come up with their electron configurations. So one thing to remember is that for an element, the atomic number Z tells us the number of protons, and if it's neutral, then that's equal to the number of electrons as well. So when you look at the periodic table and you look at the atomic number, that tells you as well the number of electrons that there are. Since we fill in the 1s shell first, we put one electron in there for hydrogen. For helium, we're going to put the second electron in that same shell until it's filled. Now that we have a third electron for lithium, we put that into the next highest energy level, and so on and so forth, until we get to the 2p subshell. Now, a note just for a notation here, the number in front represents the n principal quantum number. This represents our L value, our angular momentum, and then this represents the number of electrons that are within that subshell. So remember, each of these designations are the subshells. In this form, each of these boxes represent orbitals. So the question is, what happens when we get to carbon? We might think of two possible scenarios. One where the electrons, the next electron goes into a different orbital, or one where it goes into the same orbital. To understand which of these is the best option, we need to apply what's called Hunds Rule. And it states that in the ground state, electrons are added first as single electrons into degenerate orbitals. And then, and therefore, they partially fill the orbitals before they doubly fill them. What this does is this minimizes the repulsion between the electrons, and therefore they have lower energies. So in this scenario, these electrons are in degenerate orbitals. And so the orbital on the left, the orbital on the right are equally as energetic, and so we can put them into these separate ones and that ends up being lower than if they're paired. Because when they're paired, they repel each other more so. So it turns out that the top one is our ground state, and the bottom one would actually be an excited state. It's still possible to obtain, but it's higher energy. Hunds Rule also has some other excited states that we could get from this, and that would be if we have arrows pointing in opposite directions before we put a single one in each orbital. So if both of these are excited states, and it's also important to note that there are a couple different options for how we represent the ground state. So these are just the 2p orbitals. We could have gone and put the 2 electrons in the orbitals on the right. We could have put them so that way they are down, or any combination, so long as they're not doubly paired or opposite spins. And so each of these are also ground state representations. And the reason why they are all ground state is because, first of all, there's no difference in energy between degenerate orbitals. And all of the orbitals within the 2p are degenerate. And then secondly, spin up or spin down are the same energy. And so it doesn't matter which one you choose to go first, so long as you continue either up or down. We also have a way to simplify the presentation of electron configurations. Because what they represent is the number of electrons and where they are, imagine if you needed to write out the electron configuration of uranium or some other very heavy element. That'd get very tedious. And so what we can do is use the core notation. And that allows us to abbreviate the way that we represent things. So neon is represented as 1s2, 2s2, 2p6. Sodium is just one element, is that next element down in the periodic table, and it has one more electron. So we can use this filled shell of neon and use it as a shorthand to represent the majority of the elements that are within sodium. And so we can do this anytime we start a new row on the periodic table. While it's less useful, we could have done this as well. Helium is 1s2. And so we could have simplified beryllium as helium 2s1. It's a little bit less useful, less time-saving there, but we will see that it's actually important to think about it this way as well. And so we can represent each element as a function of the core and the valence electrons. So if we go down the periodic table, you can see the pattern. We fill up the s orbitals, and then we fill up the p orbitals. Once we get to the next completed shell, we can use that as our next stepping stone, if you will, as our next abbreviation. And so past argon, we have potassium. And so we can use argon as our core, and then just the 4s1 to represent the new row. And this gets us, again, this pattern of core or inner shell electrons represented in brackets, and the valence or outer shell electrons that are represented past that. And not only does this make it simple to communicate, it actually is useful because the core electrons do not actually participate in chemical reactions. It's only the valence electrons that do. So by using the core electron configuration notation, not only are we simplifying the process, the representation, but we're also communicating which electrons are going to be participating in chemical reactions. Let's talk about some anomalous electron configurations, and that's dealing with the transition metals. So for transition metals, you need to recognize that we're filling the 4s orbitals before we fill the 3d orbitals. And if my pen will work, I can write. We fill the 4s before the 3d. And if you take a look at the Aufbau Principle and the diagrams that we had there, that's what makes sense. However, the exceptions to this rule are copper and chromium. We would expect copper to be 4s2 3d4, and we would expect, that's chromium. We would expect copper to be 4s2 3d9. But they're not. And the reason they're not is more complicated than what we need to get into. But what you do need to know is that these are exceptions to the rule, and the main reason for these differences is because these configurations, the observed configurations, are simply lower in energy than what we would have expected. The reason for that has to do with symmetry and the symmetry of the orbitals. If you would like to know more about it, the ebook does go more in depth. But for our purposes, what's important is realizing that there are exceptions to the rule. Now that we have this in mind, let's take a look at the periodic table. Oh, one last thing before we move on to that. We talked about how the valence electrons are the ones that are involved in chemical reactions. When you have a filled subshell, then those electrons do not participate in chemical reactions. And so for transition metals, it's the unfilled 3d orbitals that are the valence electrons. So scandium, for example, has 1 valence electron. Titanium has 2 valence electrons. That's based on the 3d orbitals. Chromium has 6 valence electrons, and that's because it has 6 unfilled, or electrons, 6 electrons that are not in filled subshells. So let's take a little bit of a deeper look here at the periodic table. It's organized into what are called blocks. We have the S block, the P block, the D block, and the F block. And these blocks tell you what the valence electrons are, essentially. So within the S block, the S electrons are our valence electrons. In the D block, the D electrons are valence. Same for the P and for the F. Also, based on its location on the periodic table, you can tell how many electrons are within that given subshell. So an element here would have filled up all of the 1s, the 2s, and then has electrons left over in the 2p. Well, there's 1, 2, 3 electrons. So that would be whatever there is element right there would be 1s2, 2s2, 2p, 3. Same thing right here. We can see this would be have a p5 for its latest electrons. Right here would be 1, 2, 3, 4, 5, 6, 7, D7. And so by being able to read this off the periodic table, you can simplify the work that you need to do for determining electron configurations. So let's take a little bit more of a look here at the periodic table. It's organized not only into the blocks, the S block, the P block, the D block, and the F block, but also within them you have different categorizations. The alkali metals are our first group. The alkaline earth metals are our second group. You then have a whole array of transition metals. The halogens are the second to last group. The noble gases are the last group in the periodic table. And then you've got lanthanide and actinide metals. You also have some metals that here along this staircase that are called metalloids. And they behave similarly to both metals and nonmetals. We will see that the location on the periodic table determines the chemical properties. For example, we know that all of the alkaline metals will have a +1 charge as an ion. All the alkaline earth metals will have a +2. The third group has a +3. The halogens all have a -1, -2, and then -3. These tell us how, we'll see later that this tells us in what ways they react with each other. So by understanding the electronic structure, how many electrons there are, how many valence electrons there are, we can then predict how an element will react. And that's the whole point of understanding the periodic table, is to be able to know how things are going to interact. That's it for the content of this video lecture. I'm going to now walk you through a couple practice problems so you can watch those, and then if you have any questions on them, you can ask on Piazza. So, which of the following could represent an excited state for a neutral fluorine atom? The way we want to think about this is a couple different things. We need to recognize that we're talking about excited state as opposed to the ground state. We're a neutral element, so it's not an ion, and it's fluorine, which means that if you look on the periodic table, fluorine has 9 protons. It's neutral, so it must have 9 electrons. And so we're looking for something that has 9 electrons. We're looking for something that follows the rules, Hunds Rule, the Aufbau Principle, and does not violate the Pauli exclusion principle. So I would recommend first looking for things that might not have 9 electrons. And it turns out that A and D both have 8 electrons. So they cannot be neutral fluorine. They could be neutral oxygen, or they could be positive fluorine, or some other element with that same number of electrons, but they're not neutral fluorine. If we look at the next one here, this appears to be a violation right here. And this is a violation of the Aufbau principle. And the reason is because this electron here on the far right should be in one of those 2 orbitals first. This next one down here, it seems to follow all the rules. Even though we've put in the electrons here on these orbitals first, it doesn't matter because these are degenerate. So they have the same energy levels. So this is our ground state. And then finally, this last one, this is an impossible thing to occur, and that's because right here we have a violation of the Pauli exclusion principle. So the question is asking, what could be an excited state? Well, only B could be an excited state. We have A and D, which are not neutral fluorine. C is the ground state, and E is impossible, not excited state. Okay? Why don't you try this next one to see if you can figure it out, and then so pause the video, try it on your own, and then come back and I'll show you how to do it. All right, welcome back. We want to know which represents the lowest energy electron configuration. And if we're looking for lowest energy, again, we need it to follow all the rules. So in this first one, we can see that we're filling all of the orbitals sequentially, but then we get to here, and that's a problem. This violates Hunds Rule. which states that we would need to singly occupy all of the orbitals within a given subshell before we doubly occupy. In this, so that would give you an excited state. In the second one, we are singly or doubly occupying down here as we should. We get to 3s, and then we see that we have got electrons up here in the 3p before we filled the 3s. So this also must be an excited state. This violates the Aufbau Principle. C, going from left to right, we see it's following all the rules, except now we get to here. We've got opposite spin electrons within the same subshell. This violates Hunds Rule as well. For D, we're following it along left to right. This may appear to be a violation because, again, we've filled the middle orbital first, but remember, these are all degenerate, and so this is actually the ground state. And then finally, E, going left to right, looks good until we get to here. We see that this violates the Pauli exclusion principle, and then the rest of it appears to be correct. So D is our lowest energy electron configuration. All right, that's it for this video, folks. Thanks for watching. If you have questions, ask on Piazza or come to office hours.